Welcome to the Deep Learning for Image Analysis workshop. Okay, my name is Benjamin Wilhelm, and I'm a working student and software developer at Knime. I've worked a lot on extensions for Knime Analytics platform, including the deep learning integration. And right now I'm working more on the core functionality of Knime Analytics platform. I'm holding this workshop together with David Kolb. David Kolb, what are you doing at Knime?
Hello, everybody. So, as Benny already said, my name is David. I'm currently working in the front end and back end team at Knime, but I have been previously also working on the deep learning integrations. And I'm also personally very interested in deep learning, especially when it's about image analysis.
Okay, thank you, David. Okay, let's start then. Okay, before we start, if you have questions during the workshop, please use the Q&A section in your Zoom client. I will show a screenshot how this looks in a second. There you can also upvote your favorite question, and then we will see these questions first, and we will answer them first. And we will answer some of the questions live here, and we will answer some of the questions in the chat. And if you upvote your favorite questions, we know what questions are most important to you. So the session is recorded and will be available on YouTube. So if you miss something, you can look it up afterwards. And in the middle of the presentation is about 2 hours long, we will have a 5-minute break. Okay, this is how your Zoom client should look like, and there is a Q&A button that you can click, and then you get this Q&A window where you can ask questions. Okay, and we will then try to answer them as quickly as possible and possibly live here. Okay, and throughout the workshop, we will use Slido to ask some polls, and we would like to start with the first poll now. We would like to ask you where you are from, and for that you can take a look at in the Zoom chat. We posted the Slido link there, and you can click it and then answer. And as you can see already, some people are answering. Very cool. Okay. So many people from Germany, and I guess 2 already from Sweden. Okay. And we have many countries. Also Singapore. Oh, wow. Many European countries, but also Australia, like the United Arab Emirates. Awesome. Some people from India.
Yeah, looks very cool, Benny. Seems like we have an audience from all over the world.
Yes, that's awesome. Okay, so let's continue with the workshop. The outline of the workshop is as following. First, I will give you some motivation, why to use deep learning for image analysis. After that, we will talk about some fundamentals of neural networks and deep learning. Then David will show you how to do image classification with deep learning, and he will show you an example in Knime, which is about classifying cats and dogs. Then I will show you about semantic segmentation and show you an example in Knime of natural image segmentation. And our last part will be the most complex example. It will be about image captioning, and David Kolb will show you how this works and how he did it in Knime. So let's begin with the motivation. Get motivated to use deep learning for image analysis. So why do we want to use deep learning? And the answer is pretty easy. because deep learning works very well for image analysis tasks. Here you can see the winners of the so-called ImageNet challenge. The ImageNet challenge is an image classification challenge, and you can see that from the year 2012 on, only deep learning models won this challenge, and nothing else was able to compete. So it works really well for image classification, and it also works very, very well for many other image analysis tasks. For example, semantic segmentation, pose estimation, or even getting real looking image out of edges, often for image, or doing style transfer between images. So you can use deep learning for many of these tasks. Deep learning, however, has been around for quite some time. As you can see here on the right, we have 2012, the AlexNet, which was the first model which won the ImageNet challenge. But before that, there has been a long history with neural networks and deep learning, so the basis for all this. But only recently, deep learning gained a lot of interest. And here you can see the Google trends of the search term deep learning, and you can see a few years ago it started rising quickly, and the interest in deep learning is still very high. So what has changed? Because deep learning has been around for some time, but only recently the interest spiked. So there are two main reasons. One is the computational resources that are available now. So these graphics cards are very powerful now, and they are very well suited for deep learning. Also, we have large data sources available now, like the ImageNet dataset for the ImageNet challenge that I've shown you before. It contains 14 million images. So it's a huge data source, and this together can be used to fit these very huge models with a lot of parameters. So they are computationally expensive, and these new graphics cards are very, very well suited for them. And you need many images or many data points to generalize. But that's not always true. We will see later how we can get away with less computational resources and with less data. So, but that certainly helped to start interest in deep learning. So with the interest in deep learning, there are also many deep learning frameworks that came. And here we can see hopefully the most important ones that are available out there. And we integrated some of them in Knime. So they are marked here. So TensorFlow and TensorFlow 2, we integrated deep learning for J, Onyx, and most importantly, Keras, because Keras is used for our high level, very easy to use deep learning integration in Knime. This then looks like this. So you can easily use this Keras integration to create models. We will see later how you can design such models and how to design such models for certain tasks. Then you can learn the models and execute them as usually done with these learners and executor nodes in Knime. So that's very easy to do deep learning. Okay, now that we are motivated to use it, let's go over some fundamentals so we all know what we are talking about. Deep learning is a kind of machine learning, and machine learning means learning programs from data. There are two major kinds of machine learning. One is the supervised learning, where you have data points that have labels assigned to them. And then the task of the model is to map new data points to these labels. Examples are classifications and regression. The other major category is unsupervised learning, where you have data points without labels assigned to them. And the task of the model is then to capture some structure of the data. For example, clustering and dimensionality reduction. With this workshop, we will focus on supervised learning, because that's where deep learning is very powerful, and deep learning is straightforward to use, basically. So examples of supervised learning are mapping images to class labels, mapping a credit history to a credit score, mapping customer data to churn probability, or even mapping a lower resolution image to a higher resolution image, or mapping a cell image to segmentation of these cells. So, and you can see that 3 of these examples are actually related to image analysis, so they are interesting for us today. The basis of deep learning are so-called neural networks, and the simple neural network where everything basically starts with is the so-called multi-layer perceptron. Multi-layer perceptron looks like this. It consists of so-called layers. Here we have the input layer, a hidden layer, and an output layer. You can have multiple of these hidden layers stacked behind each other. And then a neural network, at the input layer, the data point is then present that you want to predict on. If you have a higher dimensional data point, you will have more neurons in this input layer, of course. Then the input layer is then connected to the first hidden layer, and the first hidden layer uses these neurons to compute some features on the input data. Note that you can also have more hidden neurons in here. Then you can have multiple hidden layers if you want to compute features on the features again, and to compute more higher level features. And at some point, you have the output layer, which is connected to the last hidden layer, and then computes the output from these features. Also, your output layer can have multiple neurons if you have a high dimensional output. Okay, and these neurons which compute features do look like this. So a neuron has some inputs, x1 to x3 here, and these inputs are then multiplied by some weights and added up to each other. These weights are parameters that are learned during the training of the network. So they have to be fitted to the training data. Then the sum is added to a bias, and the result of that is given to an activation function, which introduces a nonlinearity to the network. And then this is the so-called activation of the network, neuron, which is the output, and the feature basically that was computed by this neuron. For activation functions, we some examples. The sigmoid and the tangent hyperbolicals are more of the classical activation functions that were used a lot some years ago. And they have this S shape, but nowadays a lot of people just use the rectified linear units. It's a very simple activation function, just a linear function for values above 0 and 0 for values below 0, and it works very well. And I would just recommend you just to start with the rectified linear units, and then maybe you can use an enhancement of the rectified linear units, like the leaky rectified linear units, if you really want to squeeze every last bit of performance out of your model. The leaky rectified linear units are just a little different. They have a little slope for values below 0. Okay, now that we know what each neuron does, let's take a look at what the whole network does by going through the forward propagation. So we have a data point X, which is given to the input neurons. Then we compute some features on this input X with the hidden layer, so h of X. And then on these features, we compute the output of the network. But what should the output of the network be? For classification task, let's focus on that now. We want the output to be a probability distribution. So we want the probability of each class. And the probability distribution has certain properties. It has to be non-negative, and all values have to sum up to 1. So if you want to do binary classification, that's very easy to achieve. You can just use one single output neuron and use the sigmoid activation function, because it's between 0 and 1 always, and it will be just the probability of the first class. For multi-class classification, you can use the softmax activation function and use as many output neurons as you have classes, and then the softmax activation function will normalize the outputs to be a probability distribution. Okay, now if we do this forward propagation, get our probabilities, the question is this correct? And in the beginning, before we trained the network, this is not correct, because what we do is we initialize the weights that I've shown you for the individual neurons randomly, and then the network just does something in the beginning. So what we do now is we train the network, so our X is a training data point, and we actually know what the network should predict. And then we ask exactly this question, was the prediction of the network correct? So we do the forward propagation, ask this question, and we ask this question using the so-called loss function. The loss function not only tells us if the value is correct, but it tells us how far away is the model output from the true label. Loss functions to use are, for binary classification, the binary cross entropy; for multi-class classification, the categorical cross entropy; for regression, the mean squared error or the mean absolute error. But you can use other loss functions as long as they evaluate how far the model output is away from the true label. And they must be differentiable, because now we can use this loss function for the so-called gradient descent algorithm, because we want to have a very low loss, because a low loss means that our output is very close to the expected output. So we want to change our parameters, our weights, such that our loss gets lower and our model does what it's expected to do. And this is done with the gradient descent algorithm. So here we have an example. The loss function is the red function, and we have just one parameter on this x-axis. In the beginning, this parameter or weight is initialized randomly, so we are somewhere on this function. Then we use this loss function to compute the gradient of it with respect to this weight, and then we know how to adapt the parameter, or in which direction we need to adapt the parameter to get a smaller loss. Okay, and then we adapt this parameter and get a smaller loss, and we do this over and over again until we reach the minimum value where the gradient for this parameter is 0, and we don't change the parameter anymore. Remember, now we have the smallest loss available in this loss function, though that means that our network really does what it's supposed to do. To really get to the weights and adapt the weights, we use the so-called backpropagation algorithm, so to compute these gradients for all the weights, and for that that makes use of the fact that all parts of the deep learning model are differentiable, and then it uses the chain rule to compute gradients throughout the network and the gradient of the loss with respect to all of the weights of the network. So we can do this gradient descent algorithm. So this then looks like this. We have some training data X, and we input it into the network, get an output, evaluate how far it is away from the expected output. So that's our loss. And then we use our loss to compute the gradient of the loss with respect to all of the weights. And then we adapt the weights to get better or get closer to the expected output. The good thing is that we don't have to do this manually, but modern deep learning software performs this step for us automatically. So I just wanted to give you a small idea of what's happening underneath. But we don't really use just classical gradient descent. Actually, we use the so-called stochastic gradient descent, because for actual gradient descent, you would need to calculate the gradient on the full data set. And this is not really feasible for deep learning, because I told you the ImageNet dataset, for example, has 14 million images. Computing the gradient for all of these images together is very time consuming, if not even feasible. So what we do is we only take a small batch of data points and we evaluate the gradient on the small batch of data points and then adapt the model parameters. And the small batch, or the gradient of the small batch, is already very valuable for the model. So it will improve by just using this gradient. We can further improve our gradient descent algorithm by using a momentum term. Momentum term means that we average our past gradients to the current gradient and add them to the current gradient. This is like a ball rolling down a slope and accelerating because the gradient gets some speed in the direction where the gradient is always going. So this can help to reduce fluctuation. So if the gradient always goes, or would, it's a bit hot, would go in back and forth all the time, this speed can help to get it into a direction where it really matters or it changes for a long time. So it's also valuable for small but consistent gradients, and it helps to escape local minimas because you have some speed in some direction. And the loss function for deep learning is, of course, very high dimensional, not like the loss function that I've shown you, just one dimensional. And it's also not that easy, but it contains many local minima and it's very complicated. So we take everything we get to improve the gradient descent algorithm. And another thing to do that is by using an adaptive learning rate. So the learning rate controls how large the steps are taken by the gradient descent, but not all of the parameters may require the same learning rate. So we can adapt this learning rate on a per parameter basis and then get better learning for each parameter. And with these improvements, we have certain optimizers that have a little different formulations, and they are listed here. And as you can see, the last one, the atom optimizer, actually has both momentum term and the depth learning rates. And actually, I just always start with the atom optimizer because it works really well for me, and I actually just rarely change it to something else. And I would just recommend you just to start with the atom optimizer, and it will probably work already, and just change it if you are experimenting, or if you maybe want to know why change it. Okay, but now that we train our network, our true goal, of course, is to generalize the network on the task. That's sadly not what's always happening, because sometimes the model overfits to some noise in the training data. You can see this happening with the green line here in the image. And the green line perfectly separates the blue and the red dots, but it's not a very useful or very good classifier, because it does not generalize on the task. So you can see that overfitting is happening if the loss is low on the training data, so it works very well on the training data, but it does not work on new unseen data, so the test data. If this is happening, you can either decrease the model capacity, so remove some of the hidden layers, some of the neurons, and you can also use data augmentation to get more training data and to force the model to generalize. David will show you how to do some of this data augmentation techniques for images. And you can also use regularization. So for regularization, there is this old school way of just penalizing large parameters, for example, with the L1 or the L2 norm, or a combination of both. But there's also regularization that's specific to neural networks, which is called the dropout. Which is called dropout. And for dropout, you randomly drop basically some neurons during the training. So you deactivate them, and the model can then not rely on the features of these individual neurons. And this forces the network to rely more on multiple features and not on individual features. And this can also force the network to generalize better. And during inference, all the neurons are active, but they are scaled. Okay, so that are our foundations before we start with image classification. Let's go to the next question in Slido. Okay, you can see most people came from Germany. Okay, and I wanted to ask you, how familiar are you already with deep learning? Okay, there's no one yet with a lot of experience, but a lot of people with some or no experience. Okay, that's perfect, because that's basically our expected audience. Okay. I guess we have an idea. Most of you have some experience, and a lot of you also have no experience. So it's maybe good that we got some of the fundamentals now. And now I will give to David to continue, or now to ask me if there are any questions in the Q&A already that we can answer live here.
So currently there do not seem to be any questions or any open ones which you could answer live. So maybe we can wait a few more seconds and after that we could continue.
Okay. So if you have a question now, you can ask them quickly and we will answer them. Okay, yes, the workflows are already shared on the hub, and we will give you the link to the workflows, so you can go to the Knime hub and download them. And now the link to the hub is already in the chat, so you can.
Also, regarding the question about the slides, yes, the slides will be shared in the follow-up email to this workshop. So if you registered, you will receive a follow-up email and then you can look at the slides afterwards.
Okay, good.
So I think we should continue, Benny. So I will take over the screen sharing.
Thank you, David.
So the next topic we'd like to talk about is our first real application, which is about image classification. And first of all, I'd like to talk about some general things about image classification, and afterwards we jump into how this can be done in the Knime analytics platform. So what is image classification? So this task is pretty simple. So here the idea is that we have a bunch of images and we want to assign each image a class, and usually the class describes the semantics of the image. So for example, in this case, it would be classifying images into dogs or cats. How does this work or how could this work in deep learning? So usually you have to think about three parts. First is the input, how this looks like. Then here in the middle, we have the network. So we need to set up a specific network architecture to solve our task. And then we need to define how the output should look like. And let's start with looking at the input. So generally in computers, images are just represented as big arrays of numbers. And the nice thing about deep learning is that we directly can take these big arrays of numbers. We don't have to do any feature extraction on our own because this is already, so this is the idea of deep learning. So the network handles this, and we can just take the numbers and directly input them into the network, which then looks like this. Okay, nice. Next, how should the output look like? So as Benny already mentioned, for classification, we can model the output as class probabilities. So which, for example, looks like this here. So we would have, in this case, a probability vector with the length of 2, with 2 probabilities. And each index of the vector would correspond to the probability of one of the classes. And for the ground truth, in this case, we would set up the probabilities like shown on this slide. So we would have an image and the corresponding probability would be a so-called one hot vector where we just mark the position of the correct class. And we just do this for every example in our training data set and then feed this into the network. So this is basically the mapping that should be learned by the network. Then next, let's look at how we set up the network itself. So maybe you already noticed I made a small modification to this image here in the middle. So because I reduced the number of outputs or the number of output neurons to 2, because for classification you will have one neuron responsible for one of the output classes. So because we have 2 classes, our output layer will contain 2 neurons. But now the question, how do we actually perform this mapping from image to these classes? And for image classification with deep learning, this is based on two major concepts. The first one is feature extraction and the second one is information aggregation. So we need to kind of map from this high dimensional input space, so from a large amount of numbers to only 2 numbers. And I wanted to visualize this with this funnel here in between. So how can we do feature extraction? So for images, feature extraction can be done using the so-called convolution operation. So the convolution operation is a sliding window approach. where we slide a kernel over an input image. So the kernel is shown here in this shaded area and the input image in blue. And the kernel is just another array of numbers, and it's usually smaller than the input image. And then we would slide this kernel over the image, and for each window position, we calculate, we get a single number in the output. And this is done by multiplying the value in the kernel with the corresponding value in the image. Do this for all the positions in the kernel, sum it up, and then we get a number in the output. And if you slide the kernel over the input image, this would then look like this. So maybe this is a little bit hard to imagine what this does in the end. So I'd like to show you one example. So there are existing predefined kernels which can be used to extract certain features from images. So for example, there is the so-called Sobel Y kernel, and which looks like, as you can see here in the middle. This is can be used to extract or to find vertical edges in the image. And if you apply this kernel to the image on the left, we get the image on the right as an output. And here you can see that we have high output numbers and locations that correspond to vertical edges, and all the other stuff should be should have lower numbers. So you can envision a convolution as extracting certain features from images, and the features that are extracted, they depend on the numbers in the kernel. So in a deep learning network, this is done using a so-called convolution layer. And here the idea is, or the nice thing is, that we do not have to define the weights of the kernel on our own, but they are trained by the training procedure of the network. So the network learns on its own what are the best features to solve a certain task. So we don't have to do this manually. Also, because it's probably useful to extract more than one features, we have many of these kernels. So we, in one convolution layer, we usually extract many different kinds of features. So this is the first concept. Next, we have the second concept, which is about aggregation of information. This is done using a so-called pooling operation. A pooling operation is also a sliding window approach, but usually the windows are non-overlapping, and I tried to visualize this with these shaded areas here on the left. And for each of the windows, you would define a certain pooling operation. For example, we could use max pooling, which just means that we take the maximum value in one of the windows, or we could do average pooling, which means we calculate the average. And as you can already see, this reduces the dimensionality. Usually, so a common thing that is done is that we reduce the dimensionality by, so that we halve the image resolution, and this way we can aggregate the features and reduce the input space. So putting it all together, a network which uses these two concepts could look like this. So these are called convolutional neural networks, or short CNNs. And they're usually set up in the following way. So first, on the left, we have some input layer, which accepts our image inputs. Then we usually have these alternating stages between a convolution and a subsampling operation. And how many of them you use is basically a parameter, which you can try out. So there's no definitive answer. It depends on your application. So here in this case, we have one convolution, a subsampling, another convolution, and a subsampling. And after we are done with these feature extraction stages, we usually append some fully connected layer, so basically a multi-layer perceptron. And in the end, we have the output layer with as many neurons as we have classes for our task. So in our case, this looks like this. We have dog and cat images, and we have 2 output neurons. So now, after we have a rough idea how these networks look like, I also like to mention some methods that are very commonly used when we do image classification. One of them is data augmentation. So you probably might have heard that for deep learning, you usually need huge amounts of data. However, to mitigate this kind of problem, you can use data augmentation. Here, the idea is that you can create from your existing data set, you can create more ground truth data by applying so-called ground truth preserving transformations. So for example, if we have the stock image, we can mirror it, we can apply a rotation, we can blur the image, but the semantics of the image would not change. And there are many different transformations which you could think of, which you could apply, which do not change the class of your example. And this way we can create many different variations of the same image and show this to the network in the hope that this will help generalization, because then the network knows all the different versions of, for example, of the stock, and this should help, or this will help the network to generalize. And this also works very well in practice. The next method I wanted to mention, and which some even call the secret sauce, is pre-trained networks. So here the idea is that we use help, so we don't do all the heavy lifting on our own. So there are these big tech companies, for example, Google or Facebook, and they train big networks on huge data sets. And here the idea is to take these pre-trained networks and take the pre-trained features and the pre-trained weights, which extract certain features and make use of them. And this comes in different flavors. For example, we have fine-tuning. This can be used when the other task is similar. For example, we have a network trained, for example, on ImageNet, which so for the ImageNet challenge, the goal is to distinct or put images into 1,000 classes. And we can use this network as a starting point to train it, for example, on our 2-class classification. Then the second flavor would be transfer learning. This can be done if the other task differs greatly or a little bit more, so the tasks are not too similar. For example, we could use an existing network as part of our new network and even use it on a different task. So for example, here we could take ImageNet network and initialize a backbone of a semantic segmentation network, and then use this network to solve a different task and hopefully achieve better performance. And the last thing mentioned here is feature extraction. So here we just use an existing network to extract features from images. So use some internal representation of some layer of an existing network, which outputs just usually a vector of numbers. And then this feature array we can use with classical machine learning approaches, for example, random forests or gradient boosted trees or similar. So this was the part about, so this was all I wanted to say about image classification in general with deep learning. And this brings us to our first example, where we do cats and dogs classification in Knime. For this, we use the cats and dogs data set from the corresponding Kaggle data challenge. The example is or consists of 3 different workflows. First, in the first workflow, we have to do a little bit of image processing, and we do the image augmentation I previously mentioned. Then in the second workflow, we try to train a simple convolutional neural network from scratch. And then in the third workflow, we try to use this fine-tuning approach and see if we can improve our prediction quality using this approach. And we will dive straight in with the first workflow, which looks like this. So let's look at the top left part here. So here we just read in the images, so the image paths, and do some filtering, because we only want to use a subset of the cats and dogs data set for this example. Then next we have this meta node where we do the actual image processing. So here we have an image reader node which reads in the images into Knime. Then we have an image calculator node, which performs normalization of the pixel value. So in this case, we normalize between 0 and 1, which is a pretty standard technique for machine learning. And then we additionally have to bring all the images to the same size, because most networks, they require a fixed input dimensionality. Next, we perform a 80-20 split, such that we have some data which we can use for testing. Then on this top branch here, we have one more meta node to perform the image augmentation. Here, in this case, the image augmentation is performed in a Python script, because the Keras library has some nice utility methods where you can perform these kinds of image augmentations in a few lines of codes. And in this case, we input this node with 3,200 examples, and we get as output 64,000 augmented examples. So you can use this technique to really greatly enhance the numbers in your training data set. And at last, we write the prepared training and testing data to disk such that we can use them in the following workflows. Next, we'd like to train our first convolutional neural network in Knime. And the corresponding workflow looks like this. Here you maybe can already see, here in the middle, we have the Keras learner network and we have a Keras network executor. So this corresponds to the usual. So if you're already familiar with Knime, we have this usual learner and predictor pair. And if you look at the inputs of the Keras network learner, we can see it accepts the model it should train. Then in the middle input, we have the training data, and the bottom input, we have some validation data, but this is not used in this example. And now let's first look into this meta node here on the top left, and this is where we actually define the network. If you go into this, this looks like this. So here, or generally with the Knime learning integration, you can build networks also with nodes, and one node would correspond to one layer. So this is pretty simple to set up a simple convolutional neural network. In this case, we set up exactly the same network which I showed you earlier. So we have first an input layer, then we have these alternating stages of feature extraction using convolution and the pooling operation. So we have a convolution layer and a pooling layer, and we do this 2 times. Then we append some fully connected layer, so a multi-layer perceptron, and we additionally use this dropout technique previously showed by Benny. And at last, we have the output layer with as many neurons as we have classes, and we use, in this case, the softmax activation. After we defined our network, we have this middle branch here. Here we just have a table reader to read in our training data, and then we need to perform one more step, which is to convert the ground truth class to this one hot vector, which happens in this meta node. If you go into this, it gets as input table, as you can see here on the left. So in this data set, our classes are encoded as integers. So 0 would correspond to the cat class and 1 would correspond to the dog class. And all that this node is doing, it just creates the corresponding one hot vector from these classes. Also, one thing to note here is that the order of the classes we have in the one hot vector also determines the order of the classes in the output of the network. So the first probability predicted by the network would then correspond to the cat class, and the second probability would correspond to the dog class. After we read in and set up our training data and defined the network, we can use the Keras network learner to actually train it. And now we can quickly look at the configuration options of this node. So on the first tab here, on the top left, we have the input data where we assign the input of the network, the expected dimensionality you can see here on the top left part. And in this case, we have just corresponding images with this dimensionality, and we have just a column chooser to choose the input column we want to use. If you would then next, we look at the target data. Here we do the same. So our one hot vector is made up of these 2 integer columns. So we assign them here, and we can also choose the loss function you want to use here at the bottom. In this case, we use the categorical cross entropy. And then we have some further deep learning specific options. For example, we can choose the number of epochs, so how long the network should train, or we can choose the training batch size. And also we can choose these optimizers, which were already previously mentioned by Benny. So after we configured the training node how we want it, we run it and we train the network. After this is done, here in the bottom part of this workflow, we read in the training data and use a Keras network executor, which just produces for each input image in the testing data, produces the output probability. Then we still need to map these probabilities back to classes, such that we can use a scorer node, which happens in this meta node. So this meta node gets this input table, as you can see here on the left. So for example, for this first cat image, our network predicted a probability of about 92% that this is a cat. So as I already said, the first probability would correspond to the dog probability and the second to a cat probability, because that's how we set up our one hot vectors. And the network is about 8% sure that this is a cat and 92% sure that this is a 8% sure that this is a dog and 92% sure that this is a cat. And to choose the class, we just choose the one with the highest probability. And we end up with a table, as you can see here on the right. And with this data, we can directly apply a scorer node to calculate an accuracy. And if we do this, for this example, we get an accuracy of 76%, which is okay. So certainly way better than guessing, but still, I guess all of you would agree that there's much room for improvement. Thus, we go to our third and final workflow for image classification. So here we want to use a fine-tuning approach or make use of these pre-trained networks, which I already mentioned earlier. So this workflow looks very similar, or is actually, except for this part on the top, is exactly the same as the previous workflow. And here on top, this is the part where we use the pre-trained model. And this is the only change to the previous workflow. So how does this work? How can we actually fine-tune a model? So there are many ways to do this, and one way to do this is the following. So we choose an existing architecture which is pre-trained on a similar task. Then in step 2, we adapt, so we retrain only the network, so only the last layer of the network on our new task, because usually the number of output neurons has changed between the two tasks. And that's basically all that is to this approach. In Knime, this then looks like this. So first we have this DL Python network creator. This is a simple node where you can use Python code to create a deep learning network in Python. In this case, we use it to download ResNet 50, because there's again a simple keras utility function where you can download this model, this pre-trained model, with one line of code. And the ResNet 50 is just a standard, very commonly and successfully used network for ImageNet classification. So this network was originally trained on 1,000 classes. Then, because we want to do fine-tuning, we keep the whole network fixed, because we trust the features that were already pre-trained by the network. And this can be done in this keras freeze layers node, where we just mark all the layers except for the last one to be untrainable, such that the backpropagation and training procedure does not change the weights, because we trust already the pre-trained weights. Also, this improves or reduces the computational costs when training the network. Then at last, we need to exchange the output layer, because, as I said, the network was trained on 1,000 classes. So we chop away the last layer and add a new layer with only 2 classes, which happens in this add top meta node. After we did this, we proceed as usual. So read in the training data, create this one hot vector, train the network, read in the testing data, and create the output predictions. And then after that, if you look at the score, we can see now, nice, the accuracy was boosted to 94%. So one takeaway from this is that also from my own experience, that in many cases, using or making use of these pre-trained networks can be very beneficial. But of course, it depends on your use case, but it's a thing worth looking into, because usually this has some advantageous effects on your training. So with that, we are finished with the first example, which we wanted to show you. And now we are at the middle of our presentation, and we will have a 5-minute break. And while we do this, we have one more Slido question, which we wanted to ask you. And with that, I hand over to Benny.
Yes, thank you, David. It was interesting. And now we want to ask you simple, funny questions. Question: cats or dogs? What do you think? And we will continue then at, I would say, 5 after 10. Is this okay, David?
maybe we can start with the next little Q&A session, maybe 2 minutes after 11.
Okay.
So Benny, I don't know if you have any prior knowledge about the distribution of cat and dog people, if we can call it that, but it seems that it's pretty equally distributed. So
yes,
we kind of already have a perfect distribution. So there seem to be 50% of people which are into dogs and 50% into cats. And now it's even perfect. So myself, I'm a dog person. What do you like better, Benny?
Yeah, I agree with you. I also like dogs better because we had a dog. Mainly because of that, probably.
Yeah, probably that's the reason for me as well.
Yeah, dogs are just so nice. But we have a small lead for cats.
But still, I would say there's not too much rivalry going on. It's still pretty equally distributed. So Benny, I think we could start answering some questions from the Q&A.
Okay. Yes.
So maybe I can start with this question. So there was one question in the Q&A. How do you determine the number of convolutions and convolution window sizes? So this is actually a really good question, and there is not a definitive answer. So this is basically a hyperparameter of your network, and this really depends on your task. There are some best practices. So for example, I think most convolutional networks, they use a window size of 3 by 3, but there are also papers which use different sizes and also which were also able to achieve good results. So to determine the parameters, I would take the approach to look at existing networks and start with similar parameters. So look for maybe for a paper which solves a similar task than your own, and then start with these parameters. But there's no definitive answer to this question.
Yes, thank you. Another question is to quickly repeat the relationship between the term convolution and kernel. And it's basically the convolution is the operation that's done on the data, and the kernel is the parameters that are used by this convolution operation. So this kernel is then used by this convolution operation to apply the convolution. And the kernel is learned during the training. So the kernel parameters.
So maybe I can answer the question by Stefan. So he said, data subsampling, what does it exactly mean? A random combination of layers, and the network tries to find the combination that identifies the class. So if I understand correctly, so the combination of layers is not too random. So we have this pattern of convolution operations which extract features, and then the subsampling operation. And so kind of the structure is fixed, but how many of these convolution operations and subsampling operations you use depends on your specific task. And during the convolution operation, features are extracted from the image. And during the subsampling operation, we reduce the input space, because in the end, we need to arrive at only like as many numbers as we have classes. Yeah, I hope this sheds some light to your question.
Thank you, David. We also have the question if the cats and dogs example would run on a machine without a GPU in a decent amount of time. David, do you know how long this would take? I think you did run it on a GPU, right?
Yes, I can't tell you definitive numbers how long it takes, but you should be able to run it on a CPU, but maybe you will have to decrease the amount of augmented data a bit, because then it could run a long time. But it should be able to execute the network on a CPU. Okay. But of course, then you have to wait a little bit longer.
Yeah, maybe let it run overnight or something. would probably work.
So Benny, I think we should continue with.
Okay, and then answer the questions in the next Q&A section or in the chat. Okay, so then I will continue with our next topic, which is semantic segmentation. So what does semantic segmentation mean? It means assigning each pixel of an image a class. Here you can see an image with basically 4 classes. So we have some pixels that are trees, so they get the class tree. We have some monkey pixels, some fence pixels, and so on. So we segment the image and assign each pixel a class. Remember, before we did classification, for classification we used a network like this. So we did some convolutions to compute some features, and then we used subsampling to reduce the resolution of our feature maps, and then we increased our number of features by using more convolutions. And in the end, we had one output, one probability distribution, so we had one classification per image. So what we need now for the segmentation task is we need one classification per pixel, not per image. So a straightforward thing to do now is just to use what we already have and apply it on some patches of the image. And then the network should predict what the class of the middle pixel of this patch is. So we take out this patch, and the middle pixel shows a monkey. So we use this classification network and predict monkey. This patch has a tree in the middle pixel, so we predict tree. And so on. We can do this then for each pixel of the network. But the problem is that this is very inefficient because the image has many pixels, so we would run this network thousands of times. And actually, many of the computations that are happening in the network are shared or are the same between different patches because these patches overlap. So that's not a very good solution. It would work, but it's not a good way to do it. So another approach is to just use convolutional layers and just not do. I'm seeing that my audio is not good. Is this right?
For me, it's fine, Benny.
Okay. So I will continue. Okay, thank you. So we could just not do the subsampling to arrive at one prediction for the whole image or one classification for the whole image, but we could just use convolutional layers and stack them and then arrive at one classification per pixel, because our last convolutional layer could just predict this, the probabilities for each class, for each pixel. And then we could get the segmentation by getting the maximum value, of course. However, this is still not optimal because these tensors in between could become very big because they are the full size of the image. And if we add some features, this could be a lot of numbers, a lot of features, and you could have problems with GPU memory, for example. Also, another architecture just proved to be better for these segmentation tasks. And this is the so-called encoder-decoder. approach. And for the encoder-decoder approach, it looks like this. So we have an encoder part, which is the first part of this network, and which actually looks just like it does for the classification. So we compute features using convolutions, and then we do subsampling to reduce the resolution. And we do this over and over again. And at some point, we do not predict the classification, but we start with the decoding of these features. So what we do is we again use convolutions and now upsampling layers to increase the resolution again, and to get segmentation out of it. Oh, yeah, do this over and over again, and we get a segmentation. We know most of the parts of this encoder-decoder architecture, but we haven't seen any upsampling operations yet. So what you can do for upsampling is you can simply do nearest neighbor upsampling, for example, or interpolate the values. But there's also another upsampling operation, which is specific to neural networks, which is the transpose convolution. And the transpose convolution works like this. So in the bottom, you have the input image, and now we only take one pixel of the input image and multiply it by a kernel, and then add the values to to a patch of the output image. Remember, for the usual convolution, we had a patch in the input image and just one pixel in the output image. This time, we have just one pixel in the input image and the patch in the output image. So it's the other way around. And then we move our kernel, in this case, by 2 pixels to increase the resolution, and do this again for the next input pixel, and so on. And then we add up the values and arrive at our output image. This upsampling operation is very useful because the kernel weights can now be learned by the network, and therefore the network can really learn what upsampling operation is most useful to it. Okay, now we have every part, but we actually don't use the encoder-decoder architecture as it was shown before, but we use a specific encoder-decoder architecture called the UNet for our example in a second. And the UNet is, again, encoder-decoder. So you see the encoding is happening here. So we decrease the resolution and increase the number of features by using convolutions and subsampling. And then we increase the resolution again with this upconv operation, which is just the transpose convolution. And increase the resolution again and use convolutions to get the segmentation map out of it. But the important part for the UNet, or the special part, is that we also have these skip connections here. They connect the features of this layer to the features of this layer for the decoding step. So during the decoding of the features, the network has also these features available, which are of a higher resolution, because the other ones get upsampled and these ones were not downsampled. So the network is able to use these features to reconstruct high resolution details. And then we get a high resolution and very fine detailed segmentation out of it. Otherwise, these higher resolution details would get lost during the subsampling parts. Okay, let's take a look at it in Knime. So here I have a workflow prepared. You can find this workflow as every workflow on the hub with the link in the chat. Okay, and for this workflow, we do natural image segmentation. So we use the dataset, the Stanford background dataset. And this node just downloads it, and then we read it with the image reader. And the images do look like this. So it's just random natural images. Okay, we have a lot of them. And then we also need to read the ground truth data. So the segmentations, we do this in this little Python script because they are saved in a txt file that's easy to read with NumPy. So we just use NumPy to read it. And then get it into Knime. You need to fix the dimensions because they are swapped. And after that, our segmentations do look like this. Note, these are already the one-hot encoded segmentations. So we have the same resolution as the corresponding image, and then we have multiple channels. And each channel is the probability for one class for each pixel. So we have the first class in this region here, and in this region in the first image, and the second class we have in these regions, and so on. So that's a one-hot encoding in this direction. Yes. After that, we combine these segmentations and the images by finding out which correspond to each other and joining them. And then for our network, we do some image pre-processing, which is just resizing these images to a common size and also resizing the labelings to the same size, and then normalizing the images between -1 and 1 in this case to be easier to use by the network. Okay, after that, we partition the images into a train and validation data set again, and now we are ready to train on them. For that, we use a UNet, as I already said, and this time we do not define it with the layer nodes, but we define it in a little Python script. And you can use this Python network creator if you know how to write Python code, and you maybe will be quicker to write large networks in there than by using the nodes. But roughly each line here corresponds to one node in Knime. So you could also just build it with nodes. And you can see that we have the UNet here because first we do some convolutions to compute features, then we do the subsampling, so mixed pooling to decrease the resolution, do some convolutions again, and then we do this over and over again until we get to our lowest level. And then we start with the decoding by doing a transpose convolution, and so increasing the resolution again. And we also concatenate to the other features of the same layer. So the skip connection is done here. And then use convolutions again to compute useful features, and so on. We do this and arrive at our class probabilities per pixel with a softmax activation. Okay, this UNet is then trained in the Keras network learner. Just use the image as the input data, and now we have another image as the target data. So the labelings are target data, but they are just one hot encoded values. for each pixel. And we use the Atom optimizer, batch size of 4, and train for 100 epochs. So let's look how this worked. And we can see that the accuracy went up during the training and the loss went down. So this looks pretty good. And I trained this for about 2.5 hours on a GPU, not the most modern GPU, but on the GPU. Yes. Yeah. After the network is trained, we want to store it for deployment. In this case, we just tested on some validation data, but just imagine you could also do this in another workflow. So we write it to disk, and for that we add a little something to the output, basically. And because our network is predicting probability distributions for each pixel, but what we really want is the segmentations. So what we can do is we can just edit our network, edit our existing trained network, and add another layer to it. And this layer is just using the argmax function to get the class with the highest probability for each pixel. And then we create our network with the same inputs and the new output of the segmentation map. So we don't have to do this manually. Then we convert this Keras network to a TensorFlow network and save it as a TensorFlow network. We do this because TensorFlow networks are faster to execute in Knime right now because they don't need to be executed in a separate Python process, but they can be executed directly in Knime, and that's faster right now. So we use the TensorFlow network, and it's really easy to convert any Keras network to a TensorFlow network, just like this. But after that, you can't do any training anymore, but you can only do the prediction. So we read this TensorFlow network then again for deployment, and we execute it. So executing the network is basically just this node, so using the TensorFlow network executor. But remember that our ground truth data also was a one-hot encoding and not a segmentation. So to show you the results, I also wanted to have a segmentation for this, so we can compare it. And for that, we basically abuse our deep learning integration to do this for us. And we just create a network which does nothing else but the last layer that I've shown you before that was added to the other network. So the last layer which takes one hot or a probability distribution and then outputs the highest probability class. So this is this layer with the argmax function, and we do nothing else, just input this layer and output it, and then convert it to a TensorFlow network again, and use it to get our ground truth segmentation for the ground truth data with this network executor. You could also do it in other ways, but that's I just wanted to show you that you basically can do anything with these networks and can maybe abuse it to do other stuff. And in this case, we already knew how to do it, so it's just easy to use it. Okay, then we get the Knime labeling type out of it, just to be able to see it in this interactive segmentation view. And now let's take a look at the predicted segmentations. So, okay, and we can see that our network here on the left, we have the predicted segmentations already predicts pretty good segmentations. It recognizes the sky pretty well, the buildings, the road, and also the people, but it makes some errors. Here it doesn't recognize this bus completely, and it also is not as accurate as the ground truth data. We have a big blob around this person. But we can see that the network already learned what we are trying to teach it, and works pretty well already for just using a small data set and using not such long training for such a hard task. Okay, you can find screenshots of the workflow and the slides. And now, are there any new questions? And I can see that there are no open questions right now. Okay. Or do you have anything for me, David? You're muted.
Yes, sorry. I don't think so.
Okay.
Maybe we can wait some more seconds and then start with the third and last use case we wanted to show you.
Okay, so if you have a question, quickly post it and we will answer it right now. And there is one. Let me look at it. It seems okay. It seems that you need at least some Python language knowledge to set up Knime for deep learning. You need to set. Okay. You need to set up a Python environment and so on, but this is well documented on docs.knime.com. So you can also go there without Python knowledge and then set it up and just follow the instructions, and it should work. And then you can use these layer nodes to build your networks, the learner to train it, the executor to execute it. So you don't need to use Python manually. But it certainly helps if you have some Python knowledge, because then you can do more advanced things with it. Okay, why are the features not destroyed by the U-turn algorithm? U-turn algorithm? I'm not sure what this means.
So maybe so the idea of this UNet network is that we perform some aggregation in the first part and then reconstruct the image from this compressed representation. So basically that's the idea of this networks, and in practice it works very well. Maybe you could add some details to your question. And maybe you can take one more question, Benny.
Okay. Why are the resolution changes required for the training process? Without this, also training can be done. Okay, in theory it could be done, but in practice we always use these batches of training data, and for these batches we use tensors, and they just so the images just have to have the same resolution to fit in such a tensor, and this makes this also work very well on GPUs and so on. Otherwise, you would need to compute the gradients for each. Actually, it would be complicated to train on different resolution images, and so in practice, it's more useful to use the same resolution. But you can use different resolutions for the prediction, of course, in the UNet example. Okay, so let's then continue with the next part, David.
Yes, thank you. So we will now continue with the last application which we want to show you, which is about image captioning. And as I already did with the first example I showed you, I will first talk a little bit about general stuff about image captioning, and then I'll show you how this can be done in a Knime or in several Knime workflows. So probably image captioning is the least known application here. So what is image captioning about? Here the goal is to have an image and then create a textual description of this image from only the image data. So for example, for this picture here on the left, you can see some example captions here on the bottom right. And there are some specialities to this task. The first one is, so there is no one real or one perfect answer. So you could come up with many different ways to describe this picture on the left. And also if you read some of these descriptions here on the right, for example, the bottom one, some ice cream sitting next to some orange slices. So these captions are usually created by humans, and humans sometimes they make errors. So this already hints that we maybe have to do some pre-processing about that so that we do not learn these errors in the prediction. So if you look at it in the same way as we looked at it for the image classification, a nice thing would be if you could do something like this. So I just have the image input into some network architecture and then get as outputs our nice description of the image. But does this work? Unfortunately, it does. It's a little bit more complicated. It does not directly work like this. So here the problem is that usually the length of the caption, so the number of words in the caption is previously not known. So there could be 5 words describing images, or there could be 15 or 10. And in deep learning, we usually require fixed output dimensionality. So the length of the output is unknown. However, there's a simple approach, and there are many approaches to do image captioning, but we will show you the simple one, which is about that we have this iterative approach where we predict word by word. So how could this look like? So with this iterative approach, we don't only have one input to the network, but we have 2. So the first input is the image, business as usual, as we did for the image classification. And then we have a second input, which is a partial caption. So basically, this is everything we know so far. So this is part of the caption we want to ultimately predict or have the network to learn. And the output of the network is the next word in the caption. And if you model it this way, then we can set this network up just like a classification. So if we know all the words that are possible, then these words can be simply viewed as classes. So we have some vocabulary of possible words, and then the network by inputting it the image and the partial caption, it just predicts the next word in the caption. And yeah, as I said, then we have as many output neurons as we have words in our vocabulary. And one can say limitation of this approach is that we need to know all the possible words beforehand. If we look at these parts a little bit more in detail, we have again this the input 1, which is the image, and again we can directly use the array of numbers, so we know how to deal with that. Input 2 is a partial caption. So for example, a part of the caption. However, our neural networks, they can only understand numbers and they can't understand words. So how do we deal with that? And then there's a simple method to do this by just replacing each word with the index in the vocabulary. So when we create the vocabulary, we assign each word some index. The index itself does not matter as long as the index never changes while we do this image captioning, and then we just replace each word by its index, and then we have numbers which we can feed into the network. Then if you look at the output in a little bit more detail, we have a word, and as I said, this is modeled as a classification. So we again can so this is just a class. So we again can use this one-hot encoding approach to model the output of our network. So again, business as usual. So we do it the same way as we did with the image classification. To illustrate this a little bit, and also to illustrate how the corresponding training data of this iterative approach will look like, I prepared a little example. So for this one input example of our training data set, so for the image on the left and this description on the right, the corresponding training data would look like this if we put it into a table. So we have the first column where we have the input image. So in this case, the image does not change because it belongs to this one example. Then in the second column, we have all partial captions that are possible. So all partial sentences that we could build with this with our input sentence. And in the third column, we have the next word in the caption. And here you can already see that we have two special tokens. We have one start token, which is appended at, or like put at the start of the of our training example, and then one end token. And these are used, and these are used, or they are important for the prediction approach, because when after we trained our network and we have a new image where we want to know, or where we want to create a prediction, we need to input it with some partial caption. And for this, we can input it just with the start token, such that the network knows now a new sentence begins. And to know when we are done with the prediction, we need this end token. So we will keep predicting until this end token is predicted. In a little bit more detail, this iterative approach for the prediction then looks like this. So first, when we predict the caption for a new image, we predict the first word using the image as input and the start token as the partial caption. This will result in a new and in a predicted next word. Then this is concatenated with our start token, which gives us a new partial caption. And this is then again input with the same image into the network to predict the next word. And this procedure is just repeated over and over again until the network predicts the end token, and then we are done, and we just concatenate all the predicted words, and as output we get the predicted caption. Then for this approach, I'd like to show you I want to reduce the complexity a little bit of the whole model. And how can we do this? Again, we can use approaches from transfer learning and make use of these pre-trained networks, which we already did for the image classification. In particular, instead of, so you could imagine that we can append a huge, or like not a huge, but some convolutional network to extract features from the images, but because we want to keep computational complexity low, we can use pre-trained image features. So we can use an existing network and just extract features from images, and then we use this as a representation of the images in our data set. Then we can use or do a similar thing for the words. So for this, we use pre-trained word embeddings using a thing or a model that is called GLOV. And I will talk about this in a bit when I show you the example in Knime. But as an intuition, you can just view it as some feature extraction mechanisms, but not for images, but for words. And here the idea is that we do this beforehand, before we do all the training of the network, so that we can pre-calculate these image features and these GLOV features from the text, and then use this as input for the network, such that we don't have to do it during training. And the last step where we want to reduce the complexity a little bit is that we make our captions of the training data set a little bit easier using standard text processing techniques. Next, I'd like to show you how all of this works in Knime. And for the example we prepared, we used the COCO dataset. So the COCO dataset is a large image dataset for many different tasks. So there's a classification task and a segmentation task, and also image captioning task. And you can see an example of an image captioning here on the bottom. So for each image in the dataset, there are 5 alternative captions, because as I said, there's not one true answer. So we have, for each image, we have 5 targets, so to speak. And because the data set is quite large, we don't use all images, but we randomly subsample 8,000 images from the the whole data set to use for our example. Then in Knime, this example is structured in 5 workflows. So in the first 3 workflows are just some pre-processing we have to do. So in the first workflow, we make the captions a little bit simpler by doing caption pre-processing. Then in the second workflow, we calculate these image features, which I mentioned. Then in the third workflow, we do the same thing for the text. So we pre-calculate these GLOF features. Then in the fourth workflow, we actually train the model. And in the fifth workflow, we have a dedicated prediction workflow which creates the captions for new unseen images in our testing data set. And we will dive straight into the first workflow, which is about the caption pre-processing, which looks like this. So let's look at the top left part here. Here we just have a CSV reader because that's so CSV is the format where we have our captions in. We read in our captions and we convert them to documents in Knime such that we can use the text processing extension. So the output of this part here on the top would be a table like this. So we have the file name of the image and then all the captions as documents. Then in this next meta node up here, we do the caption pre-processing, which looks like this. This is done using the text processing extension. So here we perform some standard things on the caption. So for example, we convert everything to lowercase, we erase punctuation, we filter some words, and also we remove all the words which have a frequency lower than 10 to make the vocabulary easier. If you're done with that, we convert the documents back to string. And if we look at the output of this top right part, this then looks like this. We also append the start and end tokens. And then our pre-processed captions sound like this. So if you look at the first example, we have couple men riding horses top green fields. So we removed a little, so these are not grammatically perfect, but they still capture the essence. So I think everybody would still know what is going on in the corresponding image. And we do this to reduce the complexity of the task a little bit. Next, we need to create our vocabulary. So from all the words which we have, we extract all the unique words, which happens in this meta node. In this case, we end up with 1,830 unique words. And before the cleaning, we would have 10,000 words. So this really greatly helped to reduce the complexity. And remember that the number of unique words we have will correspond in the number of classes. So this also greatly reduces the number of classes which we have to predict, which makes the task easier. And then at last, we just write the vocabulary to disk to use in the later workflows. And we do the same thing for our preprocessed captions. Next, we continue with the second workflow, which is about pre-calculating the image features. So here in the top left part, we just read in our subsample of the COCO datasets. Then the calculation of the image features happens in the bottom part. Here we have this Keras network reader where we read a Inception V3 model from disk. This is again just a standard model also trained on the image net task. Then with this Keras network executor, we can actually execute the network, so we can basically extract any feature representation from any intermediate layer of the network. And in this case, we use the features of the last dense layer, so before the output layer, and this then results in some feature vector with the length of 2048. At last, we just wrap this in a Knime collection, and then the output table that is written to disk by this workflow just looks like this. So we have the corresponding image, and then just a big feature vector corresponding to the image. Next, we do the same thing, or not the same thing, but we do the pre-calculation of the features for our words using this GLOF embedding. So first of all, what am I talking about? So GLOF is a type of word embedding, and a word embedding is a method to map a word or its vocabulary index, this is actually the same, to some position in an n-dimensional space, such that the position relative to other words, will encode the semantics of the word. So maybe this is a little bit hard to imagine what this does. So I prepared a little example. So if you look at the vector for the word frog in this glove model, and if you look at the nearest neighbors of this word, so in terms of some vector distance, then the 4 nearest neighbors are the words written here. And I'm not a biologist, but if you Google this stuff, then you can actually find out that these are the scientific names of other types of frogs. So we can see that words that correspond to some kind of frog, they are placed next to each other in this vector space. So this vector space indeed seems to encode the semantics of our word. So this is exactly what we need. Then the corresponding workflow looks like this. On the top left, we have this download glove model meta node where we download this model from the internet. Actually, there are different versions, so which embed this word in different dimensionalities. So there's a 100 dimensionality one, 200, and so on. And in this case, we arbitrarily choose the one with 200 dimensions. Here in the top part, there's not much interesting stuff going on. We just construct the path on our file system such we can read it. And then the actually extraction of the features happens in the bottom part. So first we read in our vocabulary. So we want to find a feature vector for each of the words in our vocabulary. And this is done in this Python script. And all the Python script does, it just takes the glove model, looks up the vector for the corresponding word in our vocabulary, and instead of writing it to or outputting it off the node and writing it to a Knime table, we use a little trick. So we directly we create a Python dictionary and directly write this to disk, because afterwards we will need this representation later, but we will come to this in the next workflow. So now, after we are done with all the pre-processing parts, we can continue with the model training, and the corresponding workflow looks like this. And we will go through it step by step. So we will start on the left. Here we have a bunch of table reader nodes where we just read in all the data which we just created. So on top, we read in the pre-processed captions, we read in the vocabulary, and we read in our extracted image features. Then we split a tiny part of the data that we can use it for training, for testing, and write this to disk. Then we have to do some more pre-processing steps before we can actually start with the training. So as I said, because the network only can understand numbers and not words, we first need to convert our textual pre-processed captions to basically arrays of numbers. And this happens in this meta node. This meta node gets as input our pre-processed captions and the vocabulary, and all it does, it replaces every word with its corresponding index, and then we end up with something like this. The next step, which we have to do, we still have to create this iterative format of our data. So where we have the partial caption and the next token, which we did not do yet. And this happens in this Python script. If you look into it, it gets as input some metadata. So in this case, this is the maximum sequence length. So the maximum sequence length would correspond to the largest caption we have. This is used because we also need a fixed input dimensionality for the partial captions. That this also gets as input our encoded captions, so where we replaced all the words with the corresponding indices. And as output, it outputs this iterative format of our data. So we have all the possible partial captions and all the next words in 2 columns. And here one can note that in order to create a fixed dimensionality of these partial captions, we pad everything with zeros, such that each of these vectors has the same length. At last, after we created this iterative format of our data, we join it with our image features, and then we are done with preparing the data. However, we still do not know how the network should actually look like. So this is what we will look at next, and which happens in this top right part of the workflow. So, and then now let's look into this build network meta node. this looks like this. So as I said, our network has two inputs. So we have two branches. Here on the top branch, we have the image input. So first we use an input layer, which has the shape of 2048, because these are the amount of numbers which we have in our pre-calculated image vectors. And then because we already extracted features, we don't use any convolutional layers or any sort, but we just use this regularization dropout technique and then one more dense layer to a little bit process the features a little bit more. Then in the bottom branch, here's where we input the partial captions. So they have a dimensionality of 29 because this is the longest caption which we have in our data set. And then next, a very interesting part is the Keras embedding layer. So this Keras embedding layer, this can be viewed as kind of the feature extractor for text. So this Keras, this embedding layer would also creates this word embedding. But as I said, because we don't want to learn a new word embedding, we want to use a pre-trained one. That's why we can use a trick. So this layer, so all this layer would, so we want the layer to only perform this mapping from our vocabulary index to the corresponding glove vector. So we can use a little trick by using the stale Python network editor, where we can, in a few lines of code, just set the internal weights of this Keras embedding layer to our previously created Python dictionary, where we extracted the glove features and marked this layer as untrainable. So this layer will exactly perform this mapping for us. So we don't have to do it on our own. Then we continue with another dropout thingy, which is done for regularization, and we append one more LSTM layer, which is just a specialized layer type for sequence processing, but I won't go into more detail about this here. Then we fuse both branches by simply performing an add operation. So this just adds the feature maps. Then we have one more dense layer, and we have an output layer, which has the number of neurons as which is the corresponds to the number of classes. In this case, we have 1,830 classes, which is the vocabulary size. Oh, I see there's a little typo. You would have actually there should be a 3 here, and we have one more class, which is the 0 padding token, which we used for the padding of the partial captions, which we feed into this network here in the bottom branch. Okay, so now we have everything to actually train the network. We set up the data as we needed in this iterative format, and we created our network. And we can again use the Keras network learner to train the network. And let's quickly look at its configuration. So here now, because we have two inputs here in this input data tab, we can choose. We have to choose the inputs for both of the input branches of the network. So first, here the first input corresponds to the image feature, second input corresponds to our partial caption. And then we have to tell the node what data we want to use as targets. In this case, we use the target word, which is just which is our class. And maybe you noticed, but we did not yet convert our class indices of our words to a one hot vector, because we can use a little trick. So there's this conversion thing supplied by Knime, where Knime will automatically create a one hot vector from from an input column of a single number. But here you have to be cautious that this number does not run out of bounds of our shape. Otherwise, you will get an error. So, but this is just a little trick, so you don't have to create the one hot vector on your own beforehand. Then, after the model is trained, we can simply write it to disk. Now, in the last workflow, we can actually do the prediction. Here again, on the left, we read in all the stuff which we previously created. Then we calculate some metadata. So we need the index of our start token and our end token and the maximum sequence length. Then we need to prepare our test data for prediction, which looks like this. So this takes as input the index of the start token. We have the maximum sequence length and our image features, and all it does, it depends constant column. So basically, this is the first partial caption which we need to kick off the prediction. Then the actual prediction happens in this meta node using this iterative approach, which I already mentioned earlier. And in Knime, this works like this. So we start with the start seg token, we predict the next token, then we check for each of the rows which we want to predict. We check if the token is equals the end seg token. That means we are done with this example and we exclude it from the next iteration, and we repeat this whole process until we processed all of the examples. Then in Knime workflow, this looks like this. To perform this, we can use a recursive loop, which is able to route data from the end of the loop back to the start. So here this loop would get as input the test data and the trained model. Here we, in the executor in this Python script, we predict the class of the next token and map it to a vocabulary index. Then here in this row splitter, we check, are we already done? So did we already predict the end token? If yes, we route it to this top output. If not, we route it to the bottom output. And in the recursive loop end, here, everything in the top output is actually collected as output of this whole recursive loop, and everything sent to the bottom output are all the rows where we are not done predicting it, so we send it back to the start and just predict the next token. After you're done with predicting, we still need to map our, because we want to read the caption, we map the predicted indices back to words, read in the images, and then have a look at the prediction in this image viewer. And you can see some of the results here. So for example, here in the first row, it worked pretty well. So the ground truth caption you can see here on the left, and the predicted caption is clock mounted wall. So this is definitely true. If we look at some more results here on the bottom, we see that the network predicted woman eating piece of cake with fork. So there's definitely some eating going on here in this picture, but unfortunately not with a fork, but it still captures some parts of the semantics of the image. So we see that our network actually works, but there could be room for improvement. But as this is only a small example to showcase how this could work in Knime, I'm pretty satisfied with that. And with that, we are nearly at the end of our presentation, and I will hand back to Benny because we maybe have time for one more Slido thing which we can ask you.
Yes, David. We have one more Slido question, and I will share it right now. So we want to ask you what your highlight was of this workshop. And yeah, the Slido link is in the chat again. So if you don't have it open.
Yeah, Benny, I'm really interested in the answers to this question.
Dogs.
Dogs, yeah, very nice. I agree with that.
Not cats, dogs. Image segmentation and captioning. Yeah, the captioning was really interesting. Many parts and image captioning again.
Yeah, so the image captioning example is I would say the most advanced one, but it's really worth getting into it. And afterwards, if you're interested, download the workflow and go through it, maybe with the help of the slides, to really understand what's or to look at the details, because I think that's really interesting.
Mm-hmm. Okay, there are many words in that. Now it fits again in the word cloud. Image captioning, the best one. Okay, cool. We also have one more question, or not a question, one more thing to mention. So for the UNet, there are actually components on the hub since a short time, and I posted a link to the search. You can just search for UNet and component on the hub, and you can use them and then easily build your UNets with that. So that's a nice thing. Okay, and then I guess we can, I think our 2 hours are basically over. So, and most questions are already answered, and we will answer the rest in the chat. Okay, and you, before we end, you can use the promo code Deep Learning 0920 to get 20% of a Knime course, or to get the free book Knime Beginner's Luck and Words to Wisdom, from Words to Wisdom, on this link. So write down your promo code, and after that we are done with this workshop.
One more note from my side, sorry, we will also include this information in the follow-up email, so don't worry.
Okay, you don't need to write it down. Okay, so thank you for joining this webinar. I was very excited to be with you today. Okay, bye.
Goodbye, everyone. Thanks for joining.